Hello everybody, my name is Thomas Trauch. Today we are going to spend some time with Proposition VI of Leibniz arithmetic quadrature of the circle, parabola and hyperbola. And in Proposition VI, Leibniz is laying the basis for the proof of the indivisible method. And he's dividing Proposition VI in 8 different parts of a proof to do so. And in the first video of a series of videos, we're going to deal with the general construction principle first of all, which is later dubbed or named tetragonism. So let's start right away. I'm going to draw out a circle along an axis. And at this point, it's worthwhile mentioning that when you draw a circle, Leibniz is not actually just looking at this kind of circle or any curve as a geometrical figure, but actually has a very aware conception that a circle like this or any curve is a result of a physical action. So when we are dealing with these things, with the indivisible method, the method of exhaustion, and what later comes on as the infinitesimals, he never thought of these things as just purely geometrical tools to solve a geometrical problem, but he really has a deep connection with physical reality, knowing that a circle is actually nothing more than an action of a process within the universe, and the same applies to any other figure. So always keep in mind that the field Leibniz actually was coming from was physics and not mathematics. But since we are sort of relying on our senses a lot and transforming these kind of processes into planar geometry, at least for this work of Leibniz, we deal with geometrical representations of universal principles. And that's very important to keep in mind, because that actually allowed to make the jump from just trying to find geometrical solutions to a problem which is actually physical. Alright, nevertheless, let's go on. We shall place some points on the curve, and we are naming these points as can be seen C1, C2, C3 and C4. In the next steps, we are drawing the ordinates. And the ordinates have their starting point at the axis, and these starting points we shall name B1, B2, B3 and B4. So in the next step, the tetragonism was drawing out the tangents, and the tangents are drawn out in a way that they somewhere intersect the conjugate axis. So this is the axis. This is the conjugate axis. Good to keep this in mind for later constructions as well. As I said, the tangents intersect the conjugate axis, and these intersection points we call T1, T2, T3 and T4. So in another step, we are draw verticals from these tangent intersection points. Like this. And you see already we have some sort of a grid, and there's various intersection points with the verticals and the ordinates, which we shall use later to define some areas. But in the next step, before we do so, we are drawing out the secants. So you have 4 points, and 2 successive points always build a point pair. So you could connect these point pairs straight, and this thing would be called a secant. And we sort of extend the secant up to the conjugate axis such that it intersects the conjugate axis, just very similar to how the tangents intersected the conjugate axis. So we draw these out. And we name these intersection points of the secant with the conjugate axis M1, M2, and M3. And where the secant of the first point and the apex point of the circle crosses or intersects with the conjugate axis or the origin point, this point we're just going to name A because it's sort of the origin of our axis construction, and it's also the apex point of the circle. Alright, so I guess you can anticipate already from these intersection points M1, M2, M3, we also draw the verticals. So now we have a nice little grid of various intersection points between verticals and some ordinates. And in the next steps we are going to define some points which later on define some areas which we are going to compare. So the first couple of points we define is basically the intersection points of the verticals which derive from the tangents intersection points with the conjugate axis and the ordinate, and we name them D successively. So if you have a tangent originating from point C1 producing the intersection point T1 of the conjugate axis, there the vertical of this point will somewhere intersect with the ordinate of the C1 point, and this intersection point we're going to name D1. And this principle is applied to all the other points as well, so such that you produce a point D2 for the C2 point, a D3 point for the C3 point, and a D4 point for a C4 point. And in the next step we're going to define some further points which relate to the secants. So you have now a point pair which created a secant, in this case the one which produced the intersection point with the conjugate axis M1, and M1 produces a vertical which we drop down here, and this vertical is going to first of all intersect the ordinate of the first point involved in the secant, C1, and it's also going to intersect the ordinate of the second point, C2, those 2 points which produce the secant. And the intersection with the first ordinate we call N1, and the intersection point with the second point's ordinate we call P1, such that you have a succession of points like N1, P1, and the same principle for all the other point applies. So you have N2, P2, N3, and P3, and so forth if you would place more points on the curve. So now we have our little grid which is now complete, and we can now define some areas. So these are the 2 areas which we produced, and they are both based on different principles, but these principles are more or less related to each other on the basis of the originating circle figure. So we have area 1, which is this one. It's a stair-shaped area which is produced by or bound by the upper ordinate, and then the successive staircases of N1 P1, N2 P2, N3 P3, back to B4 and up to B1 again, and this is called area 1, a stair-shaped area we call it. The second area is a product of the tangents, verticals, and it's bound by the upper ordinate as well up to the point D1, and then we just connect the other D points, so from D1 to D2, from D2 to D3, and from D3 to D4, from there back to B4 again, and from there up to B1 again. So this is area 2. So, and the thing that is to be proven within this proposition is that depending on how many points you place, you can actually make the difference between these areas as small as you like. You can make it arbitrarily small depending on the number of points you put on this curve between C1 and C4. And this is basically what is called a method of exhaustion, because the more points you place on the curve, these two figures, although different in construction principle, but still relating to each other by means of the originating figure of the circle, they are going to converge into the same figure. And this is what's called the exhaustion method. And the exhaustion method is usually algebraically described by a series, a number of terms, depending on the number of points you place successively on the curve. And the more points you place, the more you converge to a final area with those two figures, the green one and the red one. And this way you kind of exhaust the series. So the lower bound areas are more or less going to define the final area of the target area, which both of these figures converge to. And this method is called the method of exhaustion. So Leibniz used that as a basis, as an example, and he used it also to derive some further steps. So he tried to find some principles which exceed the method of exhaustion, because the method of exhaustion was always based on an infinite series, which is not very convenient to handle in terms of mathematical operations. But mathematical operations was not all about Leibniz's concern, but although mathematics is just a description of what invisible physical principles dictate to us, it will never actually, mathematics will never discover principles for us. That is something that is up to our creativity. And the work of Leibniz in this case is a genius example of creativity, because by using his creativity he was able to develop the calculus, and furthermore even develop a useful means how you can actually apply the calculus in form of a mathematical operation. And that was the great achievement of Leibniz, something which Newton, who was claimed to also have found the calculus, actually never could accomplish. So this is as much as can be told to the construction principle. And it's also to be noted that, again, these areas will always be different. But the difference is you can make it arbitrarily small as you like, depending on the number of points you place on the curve. And this operation relates to the method of exhaustion. Now the next step, we're trying to demonstrate this. So I have a little slider bar down here, and with this slider bar you basically can change the number of points you place on the curve. So right now we have like 4 points, and the more I move the slider bar to the right, the more points I am going to create. See, the number of points increases, and as I increase the number of points, both curves and both figures converge to the same kind of target figure. And it's interesting to notice that if I place already about 100 points, that's actually not a lot of points on this curve, our senses really tell us that there is no difference anymore between those two figures, between figure 1 and figure 2. But knowing the construction principle, we know that there always be a difference between those two areas, and even if you place a very huge number of points on this half circular curve, you will always have a difference between these areas. So this is a very good example of that our senses are really useless at sometimes. Well, they're not useless at all, in general, but in such cases they are useless because well, our senses would tell us that these areas are equal, which in reality they're not, and we can only know by means of knowing the principle, know that they're not. All right. And it can't be stressed enough that, yes, no matter how many subsections of the part of the curve between C1 and C4 you place, the area 1 will always be different by some amount than the area 2. And when you place around 300 points on the curve, this area already sort of becomes visually equal, but because of knowing the construction principles of both curves, we know that these areas will never be equal. So this tells us something on the one hand about our senses, and it's also telling something about the capabilities of your computer. Your computer is basically doing what you tell it to do, nothing more and no less. And even if you had a nice HD screen, you wouldn't be able to distinguish between those two areas, area 2 and area 1. And this is already said before that relying merely on our senses doesn't really help science a lot. So you really need the unique capability of the human mind, namely grasping principles, physical principles, and keep them in mind even if quantities or the differences of quantities vanish. And in the very case of what later got labeled the infinitesimals, everything is basically about principle and not quantities. All right. And it's also notable that the figure which both areas converge to, this is what later gets labeled the resecting figure. And we're going to deal with the resecting figure in one of the later propositions, or even in this proposition in a different part of the proof. And at this place is also not spoken about infinity yet. It's only talked about the difference between these two areas 1 and area 2, and that this difference always prevails no matter how many points you place on the original curve. And this is something that refers to the method of exhaustion, which needs to be overcome, because that was the state of the art at the time around Leibniz, and Leibniz actually managed as quite the only one to derive a useful notation for this kind of operation, which can be expressed in a mathematical operation, although he was not originally concerned alone with mathematics, but he came from a rather physical standpoint, saying that these, what later be called the infinitesimals, namely if these distances between such two neighboring points on this curve become infinitely small, namely infinitesimals, they can only express principles, and in physical reality these infinitesimals would be analog to moments. And everyone who is interested in, I would recommend very much reading the work of Leibniz called The Dialogue on Motion and Continuity, where he is sort of in a Parmenides style dialogue, treating the very nature of motion and continuity. And those who are familiar with Plato will soon recognize that this little piece by Leibniz was consciously written very similar to the Parmenides dialogue. So much for now. This is the principle, and in the next step we're gonna get involved into the various parts of the proofs, where he's sequentially going through a couple of steps in order to show that the indivisible method as a subsequent step of the method of the ancient Greeks, the method of exhaustion, is actually true and actually provable. So much for now. I hope you will join for the other parts of the proof of this proposition, and I hope you enjoyed it a little. Thank you very much, and bye bye. Hello everybody, my name is Thomas Trautsch, and we are progressing today with the proof part 1 of Proposition 6 of Leibniz's work on the arithmetic quadrature of the circle, parabola and hyperbola. And as you may remember, in the previous video we were dealing with the construction principle of the tetragonism based on the semicircular curve. And this construction principles, there were actually two of them, one of them based on the tangents of each of these points, and the other one based on the secant of consecutive point pairs, which gave us both areas as a result. And the whole purpose of Proposition 6, as we laid out before, is the proof of the indivisible method. And Leibniz was using basically a quite different indivisible method, namely based on these resecting figure viewpoint, as compared to Cavalieri, who introduced the so-called indivisible method. But he had another approach. He was basically putting one area and another area next to it, and he said that whenever you draw a line across both of them, and then each position of the line as you move it across the area, when there's a equal length both overlapping of the line with both of these areas, if these length are equal, then the areas must be equal. And what's lacking in this viewpoint was basically what is a line. I mean, if you sum up a line with another line, knowing that the line has a codimension of 0, which basically makes the sum of many lines still 0, and you would actually never get an area. So you would, in Cavalieri's time, you still would be stuck to actually moving, instead of lines, sort of finite or rectangles, finitely slim rectangles. And this problem got only interesting once John Wallis from England in the late 17th century introduced the concept of the infinitesimals by saying that there is a dimension which has a quantity of 1 divided by infinity, 1 divided by an infinitely large quantity. And this is what Leibniz picked up on and had a very elaborate view on these things, especially in this work of the quadrature of the circle. But for now, in proof part 1, in order to get to what we just mentioned, for the purpose of Proposition 6, he needed to show first of all what the concept of the resecting figure is, and what the nature of the resecting figure is in terms of continuity, and hence we can derive some information from why the resecting figure is actually called the resecting figure. For that purpose, we start looking at, for instance, one of these little segments. Let me make this a little larger. We basically place 2 points on the curve, and we look at a single segment like this. So area 1 like this, which is later be called elementary rectangle, or the red area 2 like this, which is later called the quadrilinear area. And we look at one of these things and how are things related there by looking at 2 points only. So we place point C1 and C4, and we make our little tangent based construction. The tangent of each point intersects the conjugate axis, a vertical dropping from there, which again intersects the ordinate of the appropriate point, and this intersection would be called D, and the appropriate numbering based on the originating point. The same we do for the secant construction. We draw the secant, the intersection point M2, draw the vertical. The vertical will intersect with both ordinates of both points, and the first one we named N1 and the second one P1. And this allows us now to define the mentioned areas. So we have the elementary rectangle as part of a stair-shaped figure if you place more than 2 points on the curve, and the quadrilinear area, the red one, which are subsequent to the tangent constructional rule producing the D points. And in the next step, we are moving these points around. So and see what happens. The secant is moving, the appropriate tangent is moving, and we can state right from the beginning there, as no matter what point I move where, it is always the case that the secant of these 2 points intersects the conjugate axis always in between the points T1 and T4. And this is a major part of the reasoning why the resecting figure, which we shall have a look at in a moment, is actually named resecting figure. So that means that the vertical from originating from point M2 is always falling in between the verticals of the points T1 and T4. Alright, which also bears the consequence that the intersection points of D1 and D4 and the line N1, P1, which is a point we name F, is always falling in between the bounds of this rectangle. So no matter where or how I place these points, this will always be the case. So now Leibniz was considering something in terms of the continuity. But first of all, let's draw out the resecting figure itself. And how this is done is basically we take this point C1 here, start at the apex point of the circle, and have it moving down the entire semicircle. And what we do when we do this dynamically, we just trace the D1 point continuously and draw out the subsequent curve. And that's what we're going to do now. The resecting figure is drawing out in red now. And there we go. So, and as you can see, and which seems actually quite logical, is that when you have a construction principle like this, which is based on an originating figure which has a continuous curve, the subsequent curve must also be of continuous character. And now Leibniz was assuming an example which is actually impossible, just to demonstrate what is never going to be the case within a resecting figure that is a product of a continuous curve like the semicircle. He said that, okay, let's assume the resecting figure is not going continuously its path like this, but it's making a bend here and taking a road here and maybe also going down here, basically circumventing this rectangle which I'm framing here right now, which is later being labeled the complementary rectangle. And he said that due to the continuity or the continuous character of the originating figure being the semicircle, and the construction principle would not allow the resecting figure to have any discontinuities, like here. It doesn't stop here and then suddenly go upwards. That's not possible. And what the resecting figure never will have either is reversion points. So that means points like K or like Q, where you have an apex of a path basically circumventing this complementary rectangle. That's not possible. And he was just showing that to make sure that we know that the resecting figure bears its name because it's always bisecting this line from M2, which is falling in between the ordinates. So the resecting curve is always intersecting these vertical from M1 right between the ordinates of both points. So it's always falling, this intersection point F is always falling in this complementary rectangle. And he also gave a definition of what reversion points actually are. And he said that reversion points are basically points in which the tangent of these points becomes equal with the ordinate. Basically, what we would call today a maximum. And that is what the part one of this proof is actually the state. If we summarize it, we have a continuous originating figure being the semicircle, and by means of the construction principle we thus are only able to produce a continuous curve called the resecting curve as a product of this construction principle. And it's not going to be discontinuous, and it's not going to have any reversion points. And that is going to become important consideration for the following parts of the proof of Proposition 6. So I hope that clarifies some things for the later considerations, and I hope you stay tuned for the next video being part 2 of the proof of Proposition 6. Thank you very much, and bye bye for now. Welcome everybody. My name is Thomas, and today we are talking about proof part 2 through 8 of Leibniz's work on the arithmetic quadrature of the circle, parabola and hyperbola. And in Proposition 6 the aim is to prove the indivisible method. And the indivisible method, which Leibniz lays out here, is somewhat different from what was known as indivisible method at the time, because Leibniz sort of combined the method of exhaustion with the indivisible method. And he was doing so by basically trying to show that if you place more and more numbers of points on the semicircular curve and hence make the distance between neighboring ordinates very small, the areas which are created by it and by means of our construction principle of the tangents and their verticals from the intersection points with the conjugate axis, that they converge to one and the same figure, namely what he called the resecting figure. And the terming of this, what is to be proven, is actually very clever, because it sort of states that you can make the difference between the red area being what is named the quadrilinear shape, and the green area, which is termed the elementary rectangle. The difference between the two can be made arbitrarily small, depending on how many points you place along the semicircular curves, or in how many sort of sections you divide the semicircular curve. And that is a major difference also to the other methods of the indivisibles, that he is not actually straight looking at the figure which the aim is to quadrate, but he is sort of drawing out another figure which stands in a interesting relationship to the semicircle or the circular figure, and is trying to show that both areas, the quadrilinear shape and the elementary rectangle, converge to the very same area based on the construction principle if you place the ordinates sort of very small distances away from each other, even if you make these ordinate distances infinitely small. And by doing so, or in order to show this, he was creating another rectangle, which he termed the complementary rectangle. We have drawn this out now in blue, This is basically the rectangle where the upper left corner and the lower right corner are basically determined by the intersection points of the ordinates with the resecting figure. Yeah, the resecting figure again is actually partly being produced by the ordinates themselves, namely where these ordinates intersect with the vertical from the tangent intersection points with the conjugate axis. So hence he said that both these areas are going to converge to the same type of figure, and he said that the difference between the two can be made arbitrarily small, depending on the number of points you place on the semicircular curve. And now let's have a look at the relationship within the complementary rectangle. And there you see that it encapsulates a part of the elementary rectangle and a part of the quadrilinear figure. And both of these areas, they overlap in a certain region, which is this one between D1, F1, P1, E1. And therefore this part sort of cancels itself out when you look at it in terms of the difference between those two areas. Hence we would be able to remove this little section and we will get these two triangles, the triangle D1, N1, F1, which is the remaining part of the elementary rectangle, and the remaining part of the quadrilinear shape being the triangle of P1, F1 and D4. And you already see that these two triangles are already smaller than the complementary rectangle itself, and hence it is no problem of conceiving that the difference between those two triangles must be also smaller than the area of the complementary rectangle itself. And now the trick is to say that by placing an appropriate number of points on the semicircular curve, and by doing so making the ordinate intervals between these points or between these or its ordinates arbitrarily small, you also make the area of the complementary rectangle arbitrarily small. And because the area of the complementary rectangle is already arbitrarily small, the difference between those two triangles, which really represent the difference also between the entire quadrilinear shape in red and the entire elementary rectangle in green, this difference must also become arbitrarily small, or if you will, even smaller than arbitrarily small. And the terming arbitrarily small is actually very cleverly chosen because it does not really exclude the realm of infinity. So if you place an infinite number of points on the curve, hence making the difference between two consecutive ordinates very small or infinitely small, you also make the complementary rectangle's area infinitely small. And knowing of these differences, or this difference between those two triangles representing the difference between the elementary rectangle and the quadrilinear shape, this difference becomes smaller than infinitely small, or also infinitely small, if you will. And this signifies that because both of these figures converge toward the same figure, being the resecting figure, this actually means that you can use these entities of infinitely slim rectangles, if you will, you can treat them as lines. So not as a line in a original sense, because a line which is of a one-dimensional character, but you still use it as an area. So you have an infinitesimally slim rectangle which you treat as a line. Because that was actually Bonaventura Cavalieri's approach of defining the area by a sum of lines, which is actually not true, because when you think about it, when you sum up lines which have one dimension being 0, then you don't get an area, because summing up a lot of zeros doesn't get you an area, or doesn't open up another dimension. But rather you have to deal with the infinitesimals, and it was originating from John Wallis, who was the first one to, instead of dividing an area of interest into a bunch of lines, he was dividing it into what he called infinitesimals, or infinitely small parallelograms. And he was computing the area of interest from the sum of these parallelograms. And Leibniz took it a step further by basically sort of combining the method of exhaustion, which you can relate to as in terms of placing an infinite number of points on the semicircular curve, and therefore dissecting this semicircular curve into an infinite number of sectors and summing them up later. And in the process of summing up, instead of using lines as Cavalieri did, Leibniz uses these infinitesimally slim rectangles, which in the terminology at least he treats as lines. So, but he's always being very careful of stating that you can term them lines, or you can name them, these infinitesimally slim rectangles, you can name them lines, while they're actually not lines. They are of the same dimension as the area itself. They have one dimension in one axis, and even if infinitely small, they still have a dimension in the other axis. And it's just the case that it is in the direction of one axis, the area is infinitely small, or the component of this axis becomes infinitely small as you do so. And that's laying the very basis of his further development of the infinitesimal calculus, and it also lays the basis of his great achievement of giving the scientists and the engineers at hand an operation, a mathematically based operation, where you can treat these infinitesimals very easily. And there is actually the great achievement, and the basis for this achievement is being displayed here as proof of the indivisibles. Yeah, he was combining the method of exhaustion, the indivisible method of Cavalieri, and how it was developed further by John Wallis into something treatable in terms of getting an entity of an area, an infinitesimally slim rectangle, if you will, which you can treat as line. And like Cavalieri, he is then summing up lines, but lines which are in reality infinitesimally slim rectangles. So, and hence this is true for a single point pair and a single pair of ordinates, that the difference between those two areas, the red one being the quadrilinear area and the green one being the elementary rectangle, the difference between them can be made arbitrarily small, and it should be smaller than the area of the complementary rectangle in blue. He said that this must also be the case if you place more than one of these rectangles on the curve. So you place like 4 points on the curve. That gives you 3 ordinate pairs, all of which will create an elementary rectangle, a quadrilinear area, and a complementary rectangle. And it must be the case, because the relationship applies to all of them, that the area or the sum of the areas of the complementary rectangles will be larger always than the difference between, or the sum of the difference between the quadrilinear shapes and the rectangular, the elementary rectangles. And so the sum of the blue complementary rectangles will always be larger than the sum of the differences between the quadrilinear shapes and the elementary rectangles. And that was the basic conception, that what applies to one section or one ordinate pair, it must be also true for the sum of those. And we're trying to demonstrate this by sort of dynamically placing an increasing number of points on the circular curve, and therefore producing ever smaller ordinate intervals, which in turn produce ever smaller complementary rectangles, by applying our known construction principle of the tangents and secants of each point. And additionally, we placed on the very last complementary rectangle sort of a zoom magnifier, and the magnification factor of this sort of virtual lens or zoom objective, if you will, is increasing as you decrease the size of the ordinate interval. And this is just to show, in the very same principle as Nicholas of Cusa actually did when he was looking at Archimedes' work of the method of exhaustion in the quadrature of the circle. And then Cusa actually stated that you cannot definitely quadrate the circle by the method of exhaustion, because if you inscribe into a circle polygons with an ever larger number of corners, you may get very close to what the circle represents, but at the same time you actually make this sort of polygon shape increasingly different from the circles, because you increase the number of corners. And since the circle has no corner, and you compare it to an object which has more and more corners, instead of making this object more equal or more closer to the originating circle figure, you make it actually conceptually more different, because you introduce more corners. And this can only become round by looking at the infinitesimals, which got coined and developed by John Wallis, and then successively also by Gottfried Wilhelm Leibniz. And the point is, as I increase the number of points on the curve, as I am just doing now, you see that at some stage it must not even be a lot of points. I mean, 200 points around is not really a lot, but it's also enough to show the principle that these little complementary rectangles become already inconceivably small if you look at those being placed around the resecting figure. And but what is remaining is the principle, the relationship between the areas involved, namely being the elementary rectangle, being the quadrilinear shape, and being the complementary rectangle. So the relationship stays intact, that the difference between the red and the green area is always going to be smaller than the area of the complementary rectangle. And now we are at around 300 points, 400 points, and these rectangles appear to us as conceived by our senses as points, while the zoom magnifier is clearly showing us that we are still dealing with rectangles and the complementary rectangles and what it encapsulates in terms of the elementary rectangle and the quadrilinear shape. And this way you could actually proceed forever. You could go up as long as you like, and you could go up into infinity. You would still deal with this relationship. You can't eliminate this relationship. While you can sort of eliminate or make the quantities vanish, the principle will remain. And that is also valid for the realm of infinity. And that's the trick for the whole calculus, and that's why it works. Because the conception that the relationship between infinitesimally small areas which have a certain relationship in the finite, that the same relationship is actually valid in the infinite. And hence you can treat these areas or these ordinate intervals as lines in the infinitely. If you have this distance of the ordinate interval, or the height of the ordinate interval being infinitely small. But because not this distance not being zero, but just infinitely small, and that bears a great difference because it maintains this dimension. It maintains the dimension in which these rectangles are actually slim or infinitely small, and that makes the difference of being capable of actually summing up these infinitesimally small areas such that you don't sum up a bunch of lines, which at the end would still give you a line, because a line has a dimension of 0 in the line width, if you will. So that is the major difference. And another aspect of this viewpoint actually becomes visible as we shall draw out a little comparison. So we made the ordinate intervals to some degree conceivable now, and now we draw out the verticals from each side line of each complementary rectangle. And what you could do now is you basically could take each and every one of these complementary rectangles and drop it to the very last ordinate interval. And because we made these intervals equidistant, they will all fit into the last ordinate interval. And the sum of those complementary rectangles would basically constitute this rectangle down here, being L1, D4 and psi. And that is basically the same area as the sum of all areas of the all complementary rectangles involved. So, and by doing this, you can actually very clearly show that the principle stays intact, within these complementary rectangles, the relationships based on our little tetragonism construction principle, the relationships between the complementary rectangle, the elementary rectangle, and the quadrilinear shape. Because if we go on now placing an increasing number of points on this curve, we increase the number of complementary rectangles, and we make these complementary rectangles very small, and now it would be very tempting to think that these rectangles sort of vanish into points when it comes to the realm of infinity. And this little example here is actually clearly showing that this is not the case. So if I go above the 400 points we were introducing right now, you could go on forever until infinity, and you visually would conceive the sum of these complementary rectangles along the resecting figure as this blue line here. And it is the same, actually in the same area as the line down here. So that is clearly showing that the principle is staying intact, that you're still looking at a succession of rectangles, because the line of the resecting figure at this part, the blue line, is clearly, conceivably longer than the line down here at the bottom at the very last ordinate interval. Because we're dropping all these complementary rectangles down to the very last interval. And it shows that even if I made this number of points and the number of ordinate intervals infinitely large, you would still basically change nothing about the length of this line, or rather this succession of elementary or complementary rectangles, and it would down here always be smaller than the visually conceived line of the succession of those complementary rectangles being placed along the resecting figure. And this is because the relationship complementary, or the principal complementary rectangle, remains, as you can clearly see in our little dynamic magnifier here, which is pointing to the very last complementary rectangle at the bottom ordinate interval. And this is actually this little complementary rectangle just being magnified, in our case, like 44 times. And this line is basically longer than this line because it refers to a succession of the diagonals of the complementary rectangle, while this line refers to a succession of the complementary rectangle's width, and the width is always smaller than the diagonal of the same rectangle, and that's why this line is shorter than this line, although it is composed of the same number of the same complementary rectangles. And this is actually another demonstration or proof that principles or geometric relations stay valid, even though if you move into the realm of infinity. And hence, this is the case. It has been shown and demonstrated this way that you can treat these infinitesimally small ordinate intervals as lines, and you actually could use the areas 1 being the elementary rectangles and treat them as lines, and hence you can sort of sum these quasi-lines, or being actually infinitesimally small areas, you can sum them up just like they used to be at the time with the Cavalieri method. But this time you do it with actual areas, infinitely small areas. And this is what he was to show, and therefore he was laying the basis for the whole continued development of the infinitesimal calculus. And at the last part of this little demonstration, I would like to read out now what Leibniz wrote on the closure of this proposition, and also a little scholium which he created, which is going to tell you something about the nature of his thinking and how he was treating certain aspects of his work with regards to other people's work, especially Newton. So I'm going to read out the closure. And he wrote, this proposition needed a long stretching proof because our indivisible method is significantly different from the usual others, at least in this case. But if yet in one of these other cases being different from ours, some curve n1, n2, n3 would have been gone through these points n1, n2, n3, just as it is the case with usual indivisible methods, where curved figures are only divided into parallelograms. And he clearly refers to the method of John Wallis, who actually divided areas into infinitely small parallelograms. The proof would have been a lot easier, for the difference between the stair-shaped area n1, b1, b3, p2, n2, p1, n1, and the mixed-lined n1, b1, b3, and n3, n2, n1 would consist of the small three-lined areas n1, p1, n2, n1, and n2, p2, n3, n2, which are smaller than the rectangles n1, p1, n2, n2, p2, p3, which circumscribe them, which we shall call complementary. Thus also the mentioned difference will be smaller than the sum of those complementary rectangles. But the sum of those complementary rectangles will never be larger than the rectangles which is made by the sum of their baselines p1, n1, p2, n2, which is never larger than the line b3, n3, multiplied by the height of 1, if the heights of all of them are equal, as it is usually assumed with concurrent indivisible methods, or if it is unequal to the others with the largest. If thus the last one is said to be the largest, or at least equal to the others, the aforementioned difference will never be larger than the rectangle b2, b3, n3. Since its height can be made arbitrarily small, so can also the difference between the four-lined or the quadrilinear area 2 and the stair-shaped area 1 be made smaller than any given area. Now the sum of the elementary rectangles n1, b1, b2, p1, and n2, b2, b3, p2, and the others, etc., meaning those which form the stair-shaped area n1, b1, b3, p2, n2, p1, n1, is equal to the sum of the baselines, namely the ordinates b1, n1, b2, n2, b3, n3, multiplied by the common height, if the interval b1, b2, or b2, b3 is set as always equal. Thus we can also measure the stair-shaped area by the sum of the attached ordinates multiplied with the always equal interval between two neighboring ordinates. But the stair-shaped area can be continued as far as that the difference between itself and the mixed line, or what's referred to as the quadrilinear shape, will be smaller than any given area, as shown previously. If thus something can be proven in this form about the summation of lines and the content of a stair-shaped area, such that it is valid, however far the stair-shaped area will be continued, or that it is most valid if the intervals of the attached ordinates are sufficiently small, then it will be true for the quadrilinear shape as well, or the error, if one can be induced, will be smaller than any assignable error. Hence, it will be permitted to use the indivisible method, which progresses by stair-shaped areas or by sums of ordinates, as a strictly proven one. And this is a clear statement that he now, due to this proof of the indivisible method, is regarding these infinitely small areas of the elementary rectangles in green. He will use them as sums of ordinates, or sums of lines in his later terminology, while in reality they are still infinitely slim rectangles, if you will. Okay, and now let's move on to the scholium, which is also very interesting. He wrote, I, so Leibniz, rather would have gone over this, I would rather have overgone this proposition, because nothing is further from my mind than the over-precise pedantisms of some authors who are more interested in show than in results, for they also equally consume time for some ceremonies and have more work than understanding, and cover the origin of the discoveries which mostly seems more important to me than the discovery itself in dark clouded night. So my guess is that he was referring to guys like Newton here in this case. Since I am not denying that in the interest of geometry one possesses strictly proven methods themselves and principles of discoveries, as well as certain specifically important propositions, I had been of the opinion that the old-fashioned ways should be accounted for in some way. And this represents the end of Proposition VI, and in which we were showing that the indivisible method was actually strictly proven and now being applicable for the continued development of the infinitesimal calculus. So I hope you enjoyed the trip a little, and I'm hopefully going to see you again in the next movie, which is going to be dealing with Proposition 7. Alright, thank you for watching, and bye bye.